Hi everyone, I'm Zane. I would say I was a professional optician, but I did that for a day. Wasn't a huge fan. But I'm a telescope reviewer, writer, editor, and communications grad. I'm from Connecticut, and I just finished at the University of Connecticut. And I'm 19. I've been into astronomy for a few years, and one of the things that I did, which most people getting into the hobby do, is they get a cheap beginner scope that's terrible, and then they find out they should have done something with a better mount and maybe a little more aperture. And having spent my probably 2 years worth of goodwill at that Christmas, getting my first telescope, which was a little computerized thing that cost $500. My parents weren't exactly eager to go out and buy me another thing right away. And so I watched a video of John Dobson making a telescope mirror, and I was like, oh, I could do that. And now here I am, and people watch videos of me going, oh, I could do that. And that's a little unnerving. If you go to Reddit, which is a message board site that a lot of people use, go to our space, there's a dumb photo of me standing next to my telescope looking like I just had my soul sucked out of me. And that has got more upvotes on it than pictures of the black hole or Falcon Heavy or anything reasonable that deserves that. So I like Dobsonians. I would say I like a lot of other types of telescopes, but that would kind of be a lie. I have worked with them though. I've had something like 350 scopes now. 340? I don't know. I have a list. It's like 20 pages long. I buy and sell scopes a lot, which started as just sort of a thing to get me different equipment, but now it's just turned into a business and a way to save stuff from dumpsters. Fun fact here is, so that scope there is mine. It was originally made by John Dobson sometime in the 1980s. The rest of these scopes are all scopes made by my friends or students. That one there was made with a mirror that I started on as my first mirror, and then I put a chip in it, got upset, didn't want to work on mirrors. And my friend Anton just finished that mirror a few weeks ago and brought it to his start party. That one might look a little familiar there because it's the same thing as that. That was made by someone in Turkey and has a 3D printed focuser that's a helical non-rotating printer, really cool. That's a 16-inch that some German school crew does and brings to science, that was really cool. That's my best friend who built a 17.5-incher, and that's a 12.5-inch made by the same guy who I designed this with. Anyway, moving on. So the Dobsonian telescope is something that probably a lot of people here are at least somewhat familiar with. The basic thing is it moves up, down, left, right. It has a Newtonian optics, so it's a parabolic primary mirror and a flat secondary mirror, and you look in the side. And Dobsonians are really great for beginners and experienced users because unless you're doing astrophotography, it's pretty much the only way you're going to get a telescope above 10 inches that you can move and afford. In the case of anything 16 inches or above, good luck finding anything that's not a Dobsonian and it doesn't cost less than a house. So before Dobsonians, as some of you guys might know, the largest amateur telescopes you really saw had mirrors about 8, maybe 10 inches in diameter because they usually needed a giant metal equatorial mount that was precision machined and of course weighed several hundred pounds. I had the privilege of owning a few telescopes like that, such as the Edmund Scientific 8-inch f8, and that thing almost broke my back. That was really not portable, so the largest scopes you would ever really see would be a 6-inch, maybe an 8. And then of course, there's Schmidt-Cassegrains, which came along a little before Dobsonian got popular, and those you can get up to 10 inches before they started building. Maybe the C11. But bottom line, before the Dobsonian, the maximum one-person telescope was 8 to 10 inches. And with Dobsonians now, there are people with 20 and 16, the occasional 25-inch scope that they can keep in an SUV or a van or a trailer, which a lot of people seem to like to buy for some reason. And they're easy to aim, they're cheap, they're easy to make, and of course, since they're cheap and easy to make, inevitably they became mass manufactured. And until recently, it was the best way to get a beginner telescope was to buy a Dobsonian from a manufacturer for a couple $100, and you might get an 8-incher for $300. I'm gonna get that in a second. But the idea was that it brought big scopes that actually could show you things besides a few fuzzy deep sky objects and being able to see the planets at low power and be like, oh, I can kind of see Saturn's rings. And made it so anyone could afford that for less than the price of a phone or an Xbox. That's not really true anymore. as of now, the cheapest 8-inch telescope you can buy is $650, and that's on back order. If you want a 12-inch, $1,300 back ordered, and don't forget that's going to be the size of a water heater, and the base is made out of particle board. It weighs about 50, 60 pounds by itself, and it's this big. She actually has a 12-inch scope that I got her, and I think we can all agree that it's not exactly practical to remove. And at least that one has cutouts in the base stacked as handles. That does not. And nowadays, if you post online saying you want to make a telescope, the first response you'll get is, well, why would you do that when you can buy an 8-inch Dob for $300? Which is terribly ironic considering all this goes on the internet. That they're still out of touch. But if you go to Stellafane and you bring anything with a fast focal ratio or large aperture, you'll get sneered at, and they'll award a scope that's built a little more like a nice boat and probably costs as much because it's covered in an inch-thick layer of epoxy and made out of nice hardwoods. And again, this is not affordable to normal people. We are in the middle of, well, beginning of a recession, most likely. And of course, again, this is on back order, and this is the base price of these telescopes. You want to actually use them. Oh, well, you need at least a few eyepieces. You probably want a better finder. You're looking at probably spending another $200 on those guys. So if you want an 8-inch telescope, you're going to get pretty close to $1,000 by the time you buy it. Folding table, a chair to sit in, some eyepieces, and a case. That's before you buy books, software, anything else you might want. And today, one of the things that people seem to forget about the Dobsonian was the original point of them was to make them portable and set them up where the public was. That was why John Dobson built them. Nowadays, in a lot of places, we're fortunate here that HAC has pretty frequent outreach events that are well run. In a lot of places, if you want to go and look through a telescope, you have to go to some college observatory. It's only open during the school year, once a month, and is probably either run by people who don't know what they're doing or aren't particularly nice. One of those examples would be the Stewart Observatory at the U of A, unfortunately. And that's not going to inspire people. And more importantly, people don't know that those events exist, or they go out of their way and it's cloudy, or it's canceled, or whatever, or it's a full moon, or it's in the middle of a city. So, and then of course, inevitably they try to show them deep sky objects, etc. So, not a lot of people get to look through telescopes unless they purchase one of their own, which doesn't really help with this whole telescopes being expensive thing. Yeah, this is the current state of buying a nice scope right now. Yeah, you want a 6-inch, it's $400, which, keep in mind, filling a gas tank in a large car is about a quarter of that amount now. You know, that this isn't just something you can just casually shell out. If you want a 16-inch, well, a 16-inch is going to have a 75, unless you buy a custom-made premium scope, it's going to be a 75-pound tube, 100-pound base, and it's going to cost you $5,000 and be on backward. If you want a 24-inch, like one I built, well, first off, it's going to fill up a whole SUV or minivan. But more importantly, the base price is $20,500, and you have to custom order it and wait, potentially, I think, I talked to that guy the other day, probably around 2 years, just to get it. And that's, again, the base price. It's never that low. So if you post online asking, I want to make a telescope, I want to learn how to make my own mirrors, I can't afford to buy this stuff, I want to make my own big Dobsonian, you get some rather spicy comments. And so if you're a young person, the first place you're going to go for advice is probably going to be the internet. And when you go online and hear stuff like this, well, that's not particularly encouraging, I don't think. So the other thing, too, is that a lot of the larger telescopes get a little unwieldy. This is a 32-inch that a friend of mine has, and I love that scope. My girlfriend here, Farida, does not love that scope because it requires climbing a 12-foot ladder. It is also about 400 pounds. It doesn't actually balance because it was designed before the idea of adding large bearings to Dobsonians was a thing, so it needs a counterweight, or in this case, bungee cords, which do work, but it's a little frightening, and it's certainly not something you could set up on a regular basis. And again, if you want to buy a 32-inch telescope like this, I would say hypothetically it's probably around $50,000 to buy one new, but anywhere I looked it was $80,000. Now you might find one used if there's a lovely 30-inch f5 Dobsonian for sale right over in not Benson, it's near Wilcox, and the guy only wants $15,000 for it. It is 3 feet taller than that, and it probably won't fit in your car. Neither will the ladder. The truss poles might be a bigger problem. So really the largest telescopes you regularly see people owning that are portable is around 20 to 22 inches. Now you might see the occasional 25 inch, but it's not really practical if you use something like a 25 inch obsession. So the mirrors also take forever to cool down. The field of view is rather small, which this is manual, this is not driven. He's working on adding drives to it. The one for sale over in Wilcox is driven at least. This thing is hard to aim because you are standing at the top of the ladder, you're leaning over to look through the telrad, and you're pushing on this thing, and it has enough force pushing back at you, Newton's law, that you might fall off the ladder if you push on it hard enough to actually make it move. And obviously, you need 2 people for a scope like this. You need 2 people just to wheel it out. And you need someone to hold the ladder, and you need someone to be picking out the next target while the other person looks, which is generally how using this thing goes. Now, I love this scope, but I could not say that I would recommend this to anyone. So what's the result of this too is no one gets to look through these. These are in the middle of nowhere in somebody's private observatory or shed, and you could get sued if you invite someone over to look through it. So they don't tend to be used by clubs or the public very much because it's just impractical, especially if they don't have drives. And of course, it's just, do you really want to deal, if you have a scope like this, it's such a hassle to use in the first place. You want to be getting every minute of it to yourself, which I can understand. So there are some solutions to all these problems. Most of them are technological. Part of it is sociological, I guess. But the first one I'm going to talk about is 3D printing, and then I'm going to talk about getting discounts on mass manufactured stuff, which is also what makes the 3D printing possible for a good price tag. And then there's these meniscus mirrors, which you might be wondering what this is, and I'm going to talk about that in a second. So the first thing is 3D printing. And 3D printing is great because it's not messy. It can smell bad, and it takes forever, but it's not messy. You can mess with stuff in CAD and then just spit it out. And if you don't like it, you can mess with it in CAD and spit it out again. And the only thing you're paying for is some plastic filament, which isn't, well, it's cheaper than plywood. It's not that expensive. If you have, this is something I'm going to get to in a moment, but if you have like a library or something, or if you have a school, you can't have them messing around with power tools to build a telescope. Are you out of your mind? You can have them mess with printers. They already have them. And there's also a lot of people who aren't willing to work with power tools who will print a telescope. And that brings me to this. Now this is Hadley. Hadley is the result of 1 year of design work, mostly by my friend Jonathan Kisner. I had some impact on the mechanical design, and I picked out the optics. But I just want to make sure my numbers are correct. It's $125 to build one of these, including the optics, including 2 eyepieces. There's no finder to purchase because we print one. The optics are spherical, 4.5 inch f8, so they are basically indistinguishable from parabolic. They're very sharp. This has great views. It's not just a cheap beginner scope to show that it works. And the only thing you have to make with tools is this mount. And we're working on a printable mount where you actually have PVC pipes that you cut, and then a plastic, just top parts that you clamp to the pipe, and then a plastic disc that you really need to clamp to a board or something to make it stable enough and have a wide footprint, but it will work if you absolutely refuse to use any kind of tools. And of course, this mount here, this is a 1x6 that I cut and I stuck to a Dollar Tree picture frame and sprayed Plastidip on. And the scope has integrated bearings to pivot up and down on, this is one of the hardest things to make if you're making your own scope from scratch right here, is cutting out a nice accurate circle. This tube is open. You could cover this with fabric if you wanted, but it's just aluminum 1/2 inch poles. I made a baffle here to prevent light from shining on the mirror at a shallow angle and causing glare. And that's just craft foam that I taped to the tube. It has fully adjustable mirrors, so you can align them to perfect accuracy. And all of the hardware is embedded nuts that you don't glue. You don't have to print them in. You just drop them in. It assembles like Legos. You can do this in about 5 minutes. And then you just need to go make them out, and you need to glue the primary and secondary mirrors in place with our TV. One of my favorite things is to focus. We have a helical focuser, which you turn this knob, and this is not only extremely intuitive to someone who doesn't know how to use a telescope, but the nice thing is we don't have to worry about any small parts to make a draw tube that slides back and forth, and instead we can simply get fine motion by grabbing the outer radius here and turning it really slightly. And that actually is really surprisingly effective. And because we're also turning it this way, we don't end up moving the scope too much if you do this. And of course, like any scope, you can pop the eyepiece right out and swap it to anything you want. This is an eyepiece that costs a few dollars and you can get on AliExpress. And there's also endless customizability. You can print this in any color you want. And one of the future things is, I'll get the next slide here. We're gonna have a version that has a 2-inch Crayford focuser, which is mostly printed. And that'll also just be something you could print and bolt on any telescope. You can theoretically scale this up to about a 6-inch telescope or down to a 3-inch. So if you just have some old mirrors that are sitting around and you want to throw together a telescope with them, well, or you can't attain these exact mirrors, even though they're really easy to find, that's not a problem. You can change the design. It's super cheap. And to demonstrate to you how effective this is, there are a lot of these things in the wild, and this has only been available to the public for 2 weeks. Wow. It's on printables.com right now, and it's on the front page. That's the site for the Prusa 3D printers. And most of the people who have built these telescopes have no prior experience in astronomy or anything resembling telescope making. These are people who like to 3D print tiki heads to put on their desks, and they saw something like this, and were like, wow, a thing that actually justifies the cost of my printer. This is awesome. So you might be wondering, well, how do we make this for $125? Well, the answer is, we're not making these mirrors. First off, grinding a 4.5-inch mirror, it's smaller than my hand. I can't do it. Secondly, coating it would probably cost you $50 to $100. But if you get them on Amazon right now, they're $40, and actually this is outdated. Today they're $30. There was a Prime Day sale too. I think they went down to $25. You can get them from AliExpress if you wait a little for $21. They actually sell optics for 6 and 8-inch scopes that are really reasonably priced. You'd be hard pressed to even find used mirrors with iffy quality and iffy looking coatings for those prices. They're not perfect, but they work, and the only downside is you have to wait. You have to wait usually around 2 weeks if you order them straight from China. Now, do I love that we order these things from China? No, but if it's the difference between whether or not someone has a nice telescope that they can afford, I'm all for it. This works for eyepieces too, which is really cool. So this is a 20mm Koenig. They call it a Kellner. The 10mm is easier to find. Yeah, this is $4. You don't need to harvest eyepieces from binoculars and glue them onto a film canister. You can just get this for $4. There's also a 23mm aspheric design. It's got a wide field of view and has a plastic acrylic eye lens, which I own a full set of Tel Aviv Ethos eyepieces that cost $7,000. And I can say that little 23mm aspheric is actually really great. The only downside is it's really easy to scratch the acrylic lens. There's also this 9mm Explorer Scientific 120, which I think is $1,500 to buy from Explorer Scientific. And you can just buy the new in the box from the manufacturer for half that. Oh yeah, there's a 10mm there. Yeah, $3.81, and they have a coupon. And they may not have half the description in anything resembling legible English, but I have ordered literally hundreds of eyepieces from these people, and every single time they've showed up. I did have one eyepiece that had the lenses in it backward, but that was fine. So this sort of leads into something that this right here is part of, which is fast focal ratio telescopes. Now you might notice this scope is rather long in relation to its diameter. And what does that give you? Well, it gives you a narrow field of view in a really tall telescope if you start getting big. At this size, it makes it so that they can leave the mirror spherical and they'll still be accurate. It's easy to collimate. and your cheap $4 eyepieces are going to work real well in it. They're not going to do that at f4. They're not going to really do that at f5, which is what most of the beginner tabletop scopes that have now been jacked up to $400 are at. So why would you go so fast in focal ratio? What is possibly the advantage for visual astronomy? Well, for one thing, we can now. Coma correctors and eyepieces that have sharp fields of view out to the edge are available, and now there's even knockoffs of the ones from TeleVue that only cost $200 instead of $800 per eyepiece. So if you're okay with only having like 2 of them, you can equip yourself with some nice wide 100-degree wide-angle eyepieces and a coma corrector for $600, which that's the cost of one TeleVue Ethos. Not too bad. The other thing is that they're shorter, which means no ladders. They have wider fields of view, and they also are something that we can do with these. Now, you might be wondering, what is this weird device I'm holding in my hands? There's another thing too. With these wide-angle eyepieces, we can sort of cheat physics. You see, your eyeball can only dilate so big, so if you use too low a power with a telescope, you eventually are losing light because the little dot coming out of the scope is bigger than your eyeball's pupil, and the background starts getting bright. With these wider apparent field eyepieces, we can get more of a physical field of view at the same given power, which allows us to get wider fields of view with a fast telescope. So with an f3 telescope, you can use a 20mm eyepiece and get an exit pupil that's nearer to the limit of what your eye can dilate to, but get the maximum possible field of view. So you can see it's kind of hard to see in here, but that's my 14.7 inch, that's a 14.5 inch Dob, and that's a C14 like you might find in the observatory. And you can see the magnification is about the same, but the apparent field is larger, and the focal length of the eyepiece gets shorter and shorter the faster you go to get the same magnification. You can't find a 40mm 100-degree eyepiece because it would have a 4-inch diameter barrel and cost thousands of dollars. And the C14 won't physically handle it. So what is this? What in the world is this microwave plate doing in my hand? Which it's not a microwave plate, but it sure looks like one. Well, this is a meniscus mirror. So you might notice the back of it is convex. Because what we do is we take this flat piece of glass, we stick it over a convex mold that's been ideally ground to a convex curve made out of cement essentially, and we leave it in the kiln like this, sitting at a temperature just enough that the glass starts to melt. Not enough for the glass to flow, it just sort of moves like thick molasses or like the pitch that we use to polish these mirrors. You run it at a few hundred watts for a few days. So it may cost $100 worth of electricity for a mirror this size to slump. But the nice thing is you end up with this beautiful flying saucer here. Now, you might be wondering, why is this so thin and how can I get away with it? Well, that's the thing about this meniscus curve. This has a curve of about 0.4 inches and glass half an inch thick. So with a half-inch thick piece of glass, we end up with something that simulates a piece of glass around 1 inch thick. And therefore, I don't have to worry about all of this material out here towards the edge that's not really doing anything. We have a constant thickness, and of course, we have lightweight. Now, what are the advantages here, and why does this work? Why is this not a floppy Pringle that can't achieve a sharp image at even low power? Well, the thing is, the meniscus is sort of like a dome, and if you've ever studied architecture, you know that arches are quite a bit stiffer than a flat plate. And so some of the bending and shearing force that tends to cause issues with thin mirrors are alleviated somewhat by having this curve. The other thing is that it expands and contracts evenly. With a normal telescope mirror, when you start getting into these large sizes where the depth of the curve is an actual full 1/10 or even quarter or even half inch, the thickness of the glass towards the edge is significantly different, and even if it's only different by 1/4 of an inch, that could be several pounds or even tens of pounds of glass that are adding on at the edge. And what happens is when you have expansion and contraction, the edge that's thicker is going to have more mass, and thus it's going to expand more than the center, and as such you will no longer get a sharp image. And while you're working the mirror, it's not going to expand and contract evenly as you work it, which will induce all kinds of issues. This doesn't have that problem. As long as we support it somewhat well, which there are a variety of ways to do that, which would take me too long to explain, it's not going to deform too much. And the other thing is, it's so light, we can just grind it like a small mirror, put the mirror on top, and not have to worry nearly as much. I can do this all day. I have. I don't need a gym membership. And what's the other advantage here? Well, thick glass is not really something that anyone needs. And as such, Corning shut down the Pyrex production facilities in Elmira, New York, back around 2004. And as such, the only glass you're going to get is either going to be imported from Schott in Germany, or you're going to have to use plate glass, which plate glass is fine. It's great stuff. The manufacturing techniques for those are state of the art. They don't sell it thicker than 3/4 of an inch. You can't make a full thickness mirror or even a standard thickness, say 2-inch thick 24-incher, because the glass for it isn't available, and if you order it from Schott in Germany, they will happily sell it to you for the price of a car, or at least the price of a used car. I'd say price of a car, but actually no, I won't even get the price of a used car anymore because the used cars are crazy. But anyway, you get my point. And of course, you have to import it, you have to deal with getting it cut out of this sheet, and you have to deal with an industrial supplier and all that. It's just not worth it. And there's shipping. $250 will get you this right here. I paid $250, including shipping, from Canada. Now, if you were to do this yourself, you were to go find a tabletop. It can actually have tempered glass. It would be detempered in the melting and annealing process. You could cut out a disc of scrap glass and slump it in a kiln, and it might only cost you $50. And that's going to just be electricity and plaster. And now for a 10-inch, this is not significant savings. A 10-inch you can make out of 3/4-inch thick flat glass anyway, and the electricity cost is going to be way more than it would cost to buy a used 10-inch Pyrex blank unit. But for a 12-inch or a 16-inch or a 20-inch, well, the weight savings and the cost savings start to add up. And they're also easier to support. This can work with a 6-point flotation support, which is really easy to do. Probably best with 18 points. And you have to have this whole whiffletree thing that supports it like a waterbed. It's all fancy, but much easier to do 6 or 18 points than 27 or 54, which require working with these nightmarish little triangles that you have to cut out of sheet metal and put these little support points on. I hate it. It's horrible. Gets easier once you go bigger though. The other thing is, of course, and this is probably the most obvious one, which is why I haven't mentioned it. We've already got a curve in here. We don't have to grind this out. We don't have to turn several pounds of glass into dust. And more importantly, we don't have to exert the manual labor to do that. Which, even if you're doing it on the machine, well, if you live with other people, which I'm sure most people here do, they're probably not going to enjoy except at 900 decibels, because it sounds like a jet engine is taking off in your house, or like something's about to break, because the sharp, coarse carborundum grits you have to use to cut out the curve, especially a deep curve like this in a large mirror, are extremely loud and extremely messy. So we get to skip all that manual labor. All we have to do is smooth out the curve with some fine grits that barely make any noise at all, and most of which we can literally just pour down the sink. And then we polish and parabolize. Now, is the parabolizing of these fast mirrors easy? No. Is it easier when you can pick up the thing and don't need a crane? Yes. Is it easier when you don't have to wait 2 hours every time you make a little change to the figure to make sure that it's cooled down fully and you're measuring it accurately? Yes. Is it something that I would recommend a beginner go and do for a 20-inch? No. Not really. I mean, I would say you could do it though. A 16-inch though? Yeah, so you could do a 16-inch. You could start with a 12 or 16-inch. The not having to manually manipulate the blank through rough grinding, and also not having a 30, 40, 50, 60 pound hunk of glass that you have to deal with and wait hours for it to cool down, really helps if you're a beginner trying to learn mirror making. And of course, when you can get those cheap 8-inch mirrors off AliExpress, there's really just not any good reason to grind your own 8-inch. Now there's a bit of an elephant in the room here, which is, okay, well, how much does the rest of the scope cost? Here you go. That's happy. That's what those mass manufactured mirrors are going to cost you, including building the scope. And here are some options for up to 24 inches. And this goes bigger, by the way. The supplier who did these blanks for me can go up to 36 inches. And I got a quote today for a 45-inch blank. And I can tell you with 100% confidence it is possible to build a 40-inch telescope for less than $10,000, which you might remember was the cost of half of that 24-incher. And I think that if you have a group of people, it's going to take you less than 2 years to do that. And you could build 2 1-meter telescopes for the price of that one 24-incher, which I'm sure has very nice hardwoods and carbon fiber, but those are not what make good telescopes. It's all about the optics and whether you use it. And you can't use it if you're waiting 2 years for it to be manufactured. So I've also put some comparisons here for commercial units. So Hadley here used to be very not competitive. It wouldn't be competitive 2 years ago because a 4.5-inch Dobsonian cost $150. Why on earth would you deal with building all this when if you don't buy all the screws in big boxes, you might end up spending close to $150 on this? Well, you wouldn't, no one would do it. But it's $250 for those now, and those are on back order. And it only gets better. We can build a 16-incher for less than $1,000 and fit it in the passenger seat of a car. Or we could buy a 16-inch truss from Explore Scientific that is riddled with mechanical problems, fills up most of an SUV, and costs $3,600 and is on back order. Oh, what about a 24-inch? We can build it for $2,400 and get ourselves some eyepieces. Or pay $20,000 and wait 2 years. And climb a ladder. I've even put what cars these would fit in. So my girlfriend Farida here has a Mazda MX-5 Miata, and the telescope that this goes into is going to fit in the back of it. The Miata has slightly more internal space in the back than a large suitcase. I wouldn't fly with a 20-inch. You're going to not be able to carry it on. You could check it, but they'll probably break it. But you could fit that in a very small car. So when you look at the cost being lower, combined with the physical commitment being lower, the end result is, well, this is a 20-inch that you could carry out the door in 2 pieces and be observing within a few minutes and cram in your Prius. Or you could go buy a 20-incher that you have to buy a separate trailer for, bolt some wheelbarrow handles onto, spend 2 hours waiting for it to cool down, and then climb up a big ladder and look at a handful of things and then get tired. You're not going to use that very often. And again, this scales. I'm doing a 32-incher. I'd like to also acknowledge that I'm not the first person to do this. This is very important to me because I sound like I'm out of my mind. Because I am. However, Mel Bartels is not out of his mind because he basically invented the go-to system that powers a lot of modern Dobsonians, has written basically entire books, and has a pretty detailed website where he talks all about making these thin meniscus mirrors. And he did a 25-inch that's slightly thinner than this with a faster focal ratio 5 years ago. So if you can do that with 5 years ago worth of knowledge, whereas now there's dozens of people making meniscus mirrors like this, and with a more difficult mirror, I think I can pull it off. Tom Utvos was also one of the first people besides Mel to make a meniscus mirror, and it's worth a mention because that was actually basically his first mirror. He did a 14-inch f2.6 as his first mirror, half-inch thick, and it works. And it's also so small it needs to go on a table, which the 14-inch I did also kind of does, but I made little legs for it. I made some fast scopes, but I didn't make the mirror. So I did a 14.7-inch, which I still have. Some of you might have seen it. I did a 24-inch f3.3. Didn't really like it. It was a bit bulky. Had a full 2-inch thick mirror, 65 pounds by itself. Not exactly convenient, and not exactly in line with these. I did a 10-inch f3.2. I paid a 14-year-old kid in Australia to make that for me, and the mirror turned out wonderful. It's a great scope. I stupidly sold it. And I have a friend who did a 6-inch f3 as his first mirror, and he made it into an astrograph. He does astrophotography with it. He's discovered supernovae. Not with that scope yet, but he knows what he's doing. Come on. Hello? Is this not working? Darn. There we go. Yeah, there are a lot of other fast mirrors. So the 16.25-inch f2.6 is a popular size, 3/8 of an inch thick, weighs 6 pounds. Very cheap. There are like 5 of those being made. Mel Bartels is also now doing 42-inch f2.6s. 5/8 of an inch thick too. I'm doing the 32-inch, and I'm doing 2 of these 20-inchers. And I was doing 2 22-inchers, and I gave those to friends. And I know a guy in Ireland, he made a 6-inch f3 as his second mirror. He's doing a 12-inch So I'm doing a 20-inch. I'm just going to run by this because I don't want to spend too long on it. I'm doing two 20-inchers. One's going to be kind of for asteroid occultations and planetary imaging. The other is just a visual scope that fits in the auto. Then I'm doing a 32-inch, and I might do a 42-inch. I have a few options for glass on that. It's expensive, it's unwieldy. Is it worth it? I don't know. I'd have to build a new grinding machine. And there's some problems that start to happen. So you might recall I mentioned Mel Bartels there is doing a 42-inch f2.6 at 5/8 of an inch thick. Well, when you start going that big and that fast, the depth of the curve in the mirror is more than 5/8 of an inch. It's about 1 inch. So what happens there is the center of gravity of the mirror is actually behind this nice edge right here. So how do you support it? Well, you might be able to maybe glue it to the cell. We don't know, but it seems a sling doesn't work because a guy in Germany tried that and he cannot get it to achieve sharp images unless he points it straight up. Then there's, of course, well, why do we need to go bigger than about 32 inches? I mean, 32 inches, we can still pick up the mirror. It's 50 pounds. The scope's ladder free. It costs $5,000 or so. It's going to show you more than you're ever going to see. And what do you gain with a 42-inch? Well, you gain half a magnitude. You have a 200-pound mirror now, probably, because you need to probably beef up the thickness. There's all these issues of testing it and moving it. And you need a machine that spins at the right rate. And you have issues with the center of your mirror is going to be spinning slower, at a way different speed than the outside of the mirror at that size. You're running it on a machine. You need to run it on a machine. It's not worth it. And of course, where do you stop? Well, do we stop at 50 inches now? I mean, if we're going to do 42 or 45, do we stop at 50? Do we stop at 60? I mean, there is a guy who built a 72 with a bi-satellite mirror. Can't say it works very well, but it does work. But he was going to move it. He was going to make it portable, and now it's stuck in a suburban sky where you can't see the Milky Way. Well, it doesn't do much good there. So, is it worth it? Is it worth dealing with all these issues of supporting it? You need to start thinking about forming a group and an organization to run a 40 or, well, not a 40, but to run a 50 or 60 inch scope. You can't avoid ladders. You need a big, long building to test the mirror in. Well, I mean, it's not worth it. It's probably not worth it. I don't know. I'm probably going to come back here in 2 years and have a 60-inch blank. I don't know. We'll see. Here's a comparison here of the scopes I'm doing. I have my 14.7 inch, which that has a 3/4 inch thick conventional quartz mirror that I had done by a friend. It's really nice. Love that scope. And you can see these costs are low. And of course, only the 42 would need a ladder. And I'm thinking I would do a 45, not 42. I don't know. I haven't figured that out. Oh, you might be wondering, well, how do you get the reflective coating on these things? Don't you need to put them in a vacuum chamber? How much is that going to cost? That's going to cost a lot. You have to bring it to get it coated. You have to ship one of these. They're going to break it. You've spent hundreds of hours on this mirror, and now you have to subject it to UPS. UPS damaged the 24-inch mirror I bought. It had a big chip in it the size of my fist because they took all the packaging out for inspection. Well, what if they do that too? If you have a thinner mirror, it's just going to break in half. And what about the cost of aluminizing? Isn't the cost of aluminizing it several $1,000s by itself? Well, yeah, it is. Don't do it. You can spray silver, which might sound crazy. It's not spray paint though. Silvering was the way to go before the 1930s when John Strong invented the aluminizing process that everyone just takes for granted now. And you can build a coating chamber if you have a degree in mechanical engineering, maybe. It's not that expensive or hard, but making one big enough and good enough to do a 20 or 30 or 40-inch mirror is going to be real difficult and real expensive, and you need to store it somewhere. So you're going to end up paying to get it aluminized, and that just doesn't work. I mean, again, how are we going to build a 20-incher for $1,500 if aluminizing it is $2 grand? Well, we're not. But silvering, you see, works in a really, really cool way. What happens is you're doing a chemical reaction, essentially, that deposits a very thin layer of silver film onto the glass. Now, the old way to do this is to basically stick your mirror in a sink and pour a lot of stuff on it. And around half the time, the coating doesn't stick, or it's too thick, or something like that. And of course, we can't stick this in a sink. We definitely can't stick a 30-inch in a sink. But what we can do is we can prop it on its side, clean it, and spray it with weed killer sprayers with silver and chemicals in them. And what happens is the chemical reaction occurs as the two solutions hit the surface of the glass, and they react and deposit this thin layer onto the surface of the mirror. And now you might be wondering, wait, doesn't silver tarnish? And the answer is, yeah, it does. Something that most people don't seem to know is that usually these bigger mirrors when they have aluminum coatings, those tend to corrode because you don't have them in an airtight tube anymore. You have them in an open back cell in a scope that might be stored in a shed. It might last 10 years. You'll be lucky to get 20. So you have to think about that when you're thinking about the cost of aluminum too, because you will inevitably need to get it redone. It just might not be for a long time. And you will need to clean it too. And that's going to be a pain because you got to remove the mirror from the scope. Now silver, by default, lasts around 8 months. Not great. But there's anti-tarnishing agents, essentially lacquers that you pour on top. They deposit a thin film. It doesn't affect the shape of the mirror in a significant way. And you can squeeze the lifetime out to 1 or 2 years. You could probably push it for longer and only have minimal difference in reflectivity, but why? Just recoat it at that point. Recoating it is about an hour-long process, so it's not really much different from just cleaning a regular mirror. So you sort of get the benefit of, instead of just cleaning the car, you're just ripping out the interior of the car and replacing it for the same price of cleaning it, really. I mean, when you account for all the fluids and stuff you need to clean a mirror. And of course, you have a 99% reflective coating. You cannot achieve that with aluminum. So a 32-inch mirror with silver on it is more like a regular 34-inch. And if that regular 34-inch has been sitting in a shed for 20 years, it's more like a 30-inch silver mirror at that point. Of course, in resolution, you might have a slight difference. I don't have to worry about that. And again, once or twice a year of maintenance on a scope of 20 or 30 inches, especially when, again, we can pick this mirror up with one hand, really isn't that bad. It's better than spending $10,000 and having to cart your scope around in a trailer like it's a boat, which is what most people do. The other thing that's kind of important here, and this is what Hadley was really designed for, was doing sidewalk astronomy the way John Dobson did, which is you set up in a busy public area that's probably really light polluted and really bad, and you point the scope at the moon and try to get people to come and have a look, or the planets, maybe a double star. What's nice about Hadley is I can just go for a walk with it, carry a sign in the other hand, don't really have to worry about too much. I have John Dobson's 8-inch scope. I can't really do that. I have to make 3 trips from the car. This you could strap to your back if you wanted. You could, it's not a huge worry. And of course, if you bring the telescopes to where the people are, you are inevitably going to get way more people and a way wider variety of people than just an observatory, where they at the very least have to have the interest, time commitment, etc., to go to it, let alone know it exists. And that's really important. It's actually how I met my girlfriend here, Frida, which I didn't know anyone in Tucson when I moved to Tucson back in January, and I started setting up doing Sidewalk Astronomy, and I've made a lot of friends doing it. It gets a lot of people interested in science and space, and that's something that's pretty important. You also can make a few bucks if you have a tip jar. That can pay for your scope.
Did you 3D print that too?
No, actually, I took an orange juice card and I cut the top off. And these are some photos of me doing it in various different places with various scopes. One of the other things that people might be worried about with the future of visual astronomy is light pollution. And if you look at these terrible animations I made by screenshotting my Chrome browser, I'm sorry, these are bad. You can actually see, this is VIIRS data from 2012 to 2021. You can actually see, of course, in the dense urban areas, there's still a lot of light pollution, but in areas where there's where the main source of light pollution is actually municipal street lighting, a lot of it's gone away due to the switch to full cutoff fixtures with LEDs, which of course have the downside of not being able to be filtered out anymore. But for visual astronomy, at least, they don't have nearly as much of an effect on the night sky. And as we see things like urban densification and people being more interested in the metaverse and going outside and stuff like that, it's only going to result in less and less of these outdoor lights. Car dealerships, for instance, are a huge source of light pollution, and those aren't going to exist for much longer. I'm an IDA advocate. I actually basically run the IDA Southern Arizona chapter now because the one guy running it didn't have any interest in doing it anymore. I just did our first event last week. Please check out IDA. If you're interested in working with the Southern Arizona IDA, I basically get to represent it now, so that's cool. I have a whole bunch of bullet points here to read too, but there are a lot of things in favor of reducing light pollution that aren't astronomy related. Oregon, for example, has a program to turn off a lot of outdoor lighting for much of bird migration season, and they're actually doing a similar thing now along the Hudson River in New York, which is really exciting. They're even going to turn off the stupid Cuomo Bridge, which really needs to be renamed back. I'm a native New York City area resident. I have problems with that. Now, why is this so important? Why do I care? As a Gen Z person, I wasn't around for Apollo. I wasn't around for the shuttle. I hate the space shuttle. And thankfully, I'm not one of the people who goes on Twitter about saying space is bad because I have an existential crisis when I think about it, or I hate billionaires, which a lot of people unfortunately do. The thing is that most people don't even know we're going back to the moon in a few years' time. Artemis 1 is going to lift off next month from Kennedy Space Center and send the Orion capsule on a 1-month flight around the moon, and then in 2 years, they're going to do the same thing except with a crew of 4. And of course, SpaceX's Starship is still exploding, just so fast. I mean, the most recent one, it didn't destroy the vehicle, which is progress. They're getting ready to do an orbital flight, and of course, it's going to be the lunar lander for at least some of the Artemis missions, and at least the first landing. And it's really important to, at first, inform people that this exists, but second, have a reason to like space. Instead of them just seeing pictures on Instagram that they'll inevitably scroll past on the toilet, or see the science communication TikToks that they will also scroll past while they're on the toilet and forget about. I know a lot of science communication people who genuinely believe that making science TikToks is somehow a good use of their energy. With all due respect, people are going to scroll past it while they're sitting on the toilet to look at a cat video. It's not going to change the world. I'm sorry, it's not. But showing people an unforgettable view of the moon that's not on a screen, even if you can't show them anything else because it's from the middle of the city and it's with a scope that is janky and squeaks when you move it up and down and it's made out of printed ABS, that will change things. Especially if there are thousands and thousands of people doing it, because we can make these things for less than the price of a nice meal. And also, yes, this has happened before. Yes, we went to the moon, we had Apollo, we had a lot of people who got interested in Apollo at a young age, and many of them make up the astronomy and spaceflight community now. But there wasn't sustained public interest because people only briefly thought it was valuable. And if we don't remind people of why space is interesting, then Artemis is going to be a few flights like Apollo that then turns into either maybe at best a Mars mission that's like Apollo and we do 2 of them and then it all gets canceled, or not even that, and people go back to viewing space from the comfort of the metaverse. I don't want that future. I don't think anyone really wants that future, but that's what we're headed towards if the public isn't interested in space and astronomy. And right now, a lot of people are either completely oblivious, they are apathetic, or they actively dislike anything to do with space because of their socio-political views, or alternatively existential fears, or just straight up conspiracy theories. And as astronomers, as amateur astronomers, if we want people to be interested, not just in our hobby, but in all the things that we enjoy about space and science and technology, it's important to get younger people interested in these things while there's still the opportunity to. Young people today don't know how to use power tools, which is why Hadley is great, because it gives them the confidence that maybe they can. Just like how they aren't going to be interested in making mirrors right away. And the reality is that unless they want to pursue it of their own accord, they're not going to do it. That's true. You can't make them pay attention. But what does social media do? It shoves stuff in people's faces, and that's why people are addicted to it. This is shoving astronomy in people's faces, the way John Dobson did it, and I think that is a way to make a lasting difference. And again, you can do a little better than I did on the mount. I threw that together. I went too far. I'm kind of planning on getting a lot more stuff done with regards to astronomy outreach. I'd like to have a lot more people doing sidewalk astronomy as Artemis starts to go on, especially with all the interest in the moon. Of course, the moon is the easiest thing to show people in a telescope. It doesn't have to even be dark out. You don't have to worry about anything about conditions. The scene can be horrible, and you can just use low power and ignore the slight fuzziness. It doesn't matter. It's up most of the year, and of course, people know what it is. Okay, that's not true. That is genuinely not true. That's a lie. I have met people who genuinely get confused as to where the moon is in the sky, or are like, what's that? And then I get worried, and that's why I believe in this stuff so much. There are already around 50 of these scopes in the wild, and they've been out online for less than a month. And again, most of the people making them aren't people who already make telescopes. I don't think any of them are. I don't even think most of them aren't even people who already have telescopes. This is their first. And a lot of them might not have ever gotten interested if they hadn't seen it on the Prusa site. One of the other things I do is I give out glass. I'd like to thank Eric Allen, he's not here, but he just gave me a pile of books on top of a pile of glass and a mirror making machine. I've given out something like 1,000 finished mirrors and mirror blanks. That big lot there and that one picture is I went to Stellar Vision in Tucson and bought every single mirror that the guy had collected over 40 years from the store and filled up my minivan and then brought it home and nailed out every single one of them. Is that sustainable? No, but I saved a lot of mirrors from going in a basement. That's gotten a lot of people interested. To show you, here are some of the people who have been building scopes who I personally know, most of them with stuff I gave them, or with, there's another Hadley, I love that one, it's held together with clamps. That's one of my friends making a mirror. That one's most recent, that's someone I know. I gave him 2 6-inch mirror blanks, he's in Ireland, and he made a 6-inch, that's a stovepipe for a tube. And now he has a mirror making machine and he's working on a 12-inch meniscus. That's all I have. I have a lot of links here. Reddit and Discord are really some of the main places now I participate in a lot of astronomy discussion. They are a little strange platforms, but they work, and that's where I met the guy who I designed this with. I'd really like to thank John for doing this, because I can't use CAD for the life of me. It's just mindless power tool usage, which is why I have a scar on my thumb. But yeah, that's about all I have. So, I'd like to note, this link here will take you to a giant list of equipment I have that you could buy from AliExpress. Even if you're not planning on building a scope, there are eyepieces, filters, cameras, bino viewers, diagonals, laser pointers. One of my favorite things is the cheap green laser, the green laser pointers that you can buy for like $4, and they're way better than the little pen ones. They do need a lithium battery. And I also have the link here to Hadley. You can also just search Hadley Principal Telescope, it'll probably come up. It's named after John Hadley, who invented the first practical Newtonian reflector. Newton made a telescope that was a proof of concept, didn't really work, didn't have a parabolic mirror, and then he just moved on to sniffing mercury, because he did a lot of that. Hadley came along and figured out how to test mirrors by pointing them at stars and looking at diffraction patterns, and he made a Newtonian reflector that was actually very similar in capabilities to this thing. It had a metal 6-inch mirror, and with 66% reflectivity, it would have performed similarly to this, and I can't imagine it was perfect, though. It was certainly not terrible. So I imagine the views through his telescope are very similar to our Hadley here. And I hope he would have liked it.
Well, Zane, does anybody have any questions? I know this came at you very, very